Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Celestial gatherings. The mysteries of star clusters. Star clusters, one of the most enchanting phenomena in the night sky, are celestial gatherings of stars bound together by mutual gravitational attraction. These clusters are not mere accidental groupings but are born from the same stellar nurseries, sharing common origins and chemical compositions. They offer a unique window into the formation, evolution, and ultimate fate of stars, enriching our understanding of the cosmos. When gazing at the night sky, the myriad stars scattered across the celestial sphere seem to form random patterns. However, amidst this stellar tapestry, there are regions where stars congregate more densely. These regions, known as star clusters, come in two primary forms: open clusters and globular clusters. Each type has distinct characteristics and tells a different story about the life cycle of stars and the dynamics of our galaxy. Open clusters are loose, irregular collections of young stars, typically found in the galactic plane of the Milky Way. These clusters are relatively small, containing a few dozen to a few thousand stars. They are often enshrouded in remnants of the molecular clouds from which they formed, giving birth to some of the most luminous and massive stars in the galaxy. The Pleiades, also known as the Seven Sisters, is one of the most famous open clusters. Visible to the naked eye, the Pleiades cluster is a captivating sight, showcasing a group of hot, blue stars that have formed relatively recently in astronomical terms. The stars in open clusters are loosely bound by gravity, making them susceptible to dispersal over time. As they orbit the galactic center, interactions with other stars and molecular clouds can strip stars away from the cluster, eventually leading to its dissolution. Despite their ephemeral nature, open clusters play a crucial role in our understanding of stellar evolution. Since all the stars in an open cluster formed at roughly the same time, they serve as natural laboratories for studying the early stages of star development. By comparing the different stages of stars within a single cluster, astronomers can glean insights into the processes that govern stellar birth, maturity, and death. In contrast to the youthful exuberance of open clusters, globular clusters represent the elder statesmen of the galaxy. These ancient, densely packed spheres of stars contain hundreds of thousands to millions of stars, tightly bound by gravity. Globular clusters orbit the galactic core in the halo of the Milky Way, far from the bustling activity of the galactic plane. Their stars are predominantly old and metal-poor, meaning they formed early in the history of the universe before heavier elements were widely available. One of the most striking aspects of globular clusters is their remarkable stability. Despite their immense age, many globular clusters have remained intact for billions of years, surviving the tumultuous environment of the galaxy. This longevity allows astronomers to use globular clusters as cosmic time capsules, offering a glimpse into the conditions and processes that prevailed in the early universe. By studying the ages, compositions, and dynamics of stars within globular clusters, scientists can reconstruct the timeline of galaxy formation and evolution. Globular clusters are also fascinating in their diversity. While many appear similar at first glance, each cluster has its own unique characteristics, influenced by its formation history and subsequent interactions with the galaxy. Some globular clusters exhibit multiple populations of stars with different chemical compositions and ages, suggesting complex formation histories involving multiple episodes of star formation. These findings challenge our understanding of globular cluster formation and hint at the intricate interplay between stars and their environment. The study of star clusters is not confined to our galaxy alone. Observations of nearby galaxies, such as the Andromeda Galaxy and the Magellanic Clouds, reveal rich populations of both open and globular clusters. By comparing clusters in different galaxies, astronomers can explore how the properties of star clusters vary with galactic environment. These extragalactic clusters also provide a valuable benchmark for understanding the similarities and differences in star formation and evolution across the universe. One of the key tools in the study of star clusters is the Hertzsprung-Russell (HR) diagram, a graphical representation of the relationship between the luminosity and temperature of stars. When plotting the stars of a cluster on an HR diagram, a clear pattern emerges, known as the main sequence. The position of a star on the main sequence provides crucial information about its mass, age, and evolutionary stage. By analyzing the main sequence turn-off point, where stars begin to leave the main sequence and evolve into red giants, astronomers can estimate the age of a star cluster. This method has proven invaluable in determining the ages of both open and globular clusters, helping to piece together the chronology of stellar and galactic evolution. The dynamical evolution of star clusters is another area of intense research. Over time, gravitational interactions between stars within a cluster can lead to energy exchange, causing some stars to gain velocity and escape the cluster while others move closer together. This process, known as dynamical relaxation, gradually alters the structure of the cluster. In globular clusters, this can lead to core collapse, where the central region becomes extremely dense, potentially forming a central black hole. Observations and simulations of star cluster dynamics provide critical insights into the interplay between gravitational forces and stellar evolution, enhancing our understanding of both individual clusters and the broader galactic context. In recent years, advances in observational technology have revolutionized our ability to study star clusters. High-resolution imaging from space-based telescopes like the Hubble Space Telescope, the James Webb Telescope, and ground-based observatories equipped with adaptive optics have unveiled unprecedented details of cluster structures and individual stars. Spectroscopic studies, which analyze the light from stars to determine their chemical compositions and velocities, have revealed intricate patterns of element abundances within clusters, shedding light on the processes of nucleosynthesis and chemical enrichment. The advent of large-scale sky surveys, such as the Gaia mission, has provided a wealth of data on the positions, motions, and properties of millions of stars, enabling precise measurements of star cluster distances and motions. These data have revolutionized our understanding of the Milky Way's structure and dynamics, allowing astronomers to trace the orbits of star clusters and reconstruct their histories. Gaia's unprecedented precision has also led to the discovery of numerous new star clusters, expanding our inventory of these celestial gatherings and providing fresh opportunities for exploration. Star clusters also play a crucial role in the study of stellar populations and galactic archaeology. By examining the properties of clusters with different ages and metallicities, astronomers can reconstruct the star formation history of the Milky Way and other galaxies. This approach, known as stellar population synthesis, involves comparing the observed properties of clusters with theoretical models to infer the past rates and patterns of star formation. By piecing together this puzzle, scientists gain insights into the processes that shaped galaxies and the interplay between stars, gas, and dark matter. One of the most intriguing aspects of star clusters is their potential to host exotic objects and phenomena. In dense environments like globular clusters, the close proximity of stars increases the likelihood of interactions and collisions. These interactions can lead to the formation of binary star systems, where two stars orbit a common center of mass, as well as more exotic objects like blue stragglers, millisecond pulsars, and X-ray binaries. Blue stragglers are stars that appear younger and more massive than their counterparts in the cluster, likely formed through mergers or mass transfer in binary systems. Millisecond pulsars are rapidly rotating neutron stars that have been spun up by accreting material from a companion star. X-ray binaries are systems where a compact object, such as a neutron star or black hole, accretes material from a companion, emitting X-rays in the process. These exotic objects provide unique laboratories for studying extreme physics and stellar evolution. The study of star clusters is not limited to professional astronomers. It also captivates amateur astronomers and stargazers. Many star clusters are visible to the naked eye or through small telescopes, offering a glimpse into the beauty and complexity of the universe. Observing star clusters can be a deeply rewarding experience, connecting us to the broader cosmos and sparking curiosity about the processes that govern the birth and evolution of stars. As we continue to explore the cosmos, star clusters remain a focal point of astronomical research, offering invaluable insights into the nature of stars, the dynamics of galaxies, and the history of the universe. From the glittering jewels of open clusters to the ancient relics of globular clusters, these celestial gatherings illuminate the intricate tapestry of the night sky, reminding us of the profound connections that bind us to the stars. The study of star clusters not only deepens our understanding of the cosmos but also inspires a sense of wonder and awe at the grandeur of the universe. As our knowledge and technology advance, the mysteries of star clusters continue to unfold, revealing new layers of complexity and beauty in the ever-expanding quest to comprehend the cosmos.